We did matched pairs last class. We're going to kind of completely switch gears and do the last and final topic. Now, there's a couple things within the topic, but it'll be the last thing that we kind of cover before the final. All right, so we'll probably do it today. Next Monday and Wednesday, we'll work a little bit more on it. And then that following Monday, we will still meet if you want to. I'll just be doing some exam review that Monday of finals week. But I believe up on, let's see if this will update. Let's reload. All right, so if we go under files and final exam materials, I've got a practice exam up there with the formula sheet already. I'll get a second one up there. I had a lot of things that come up unexpectedly this week, so I should be able to get around to this tomorrow. I'll get kind of that second practice exam up there. You can already start kind of reviewing at least the problems that look like the material we've already covered. And then some of the material won't look very familiar, and that's going to be all this regression stuff that we're going to be looking at. Okay. So we've been doing hypothesis testing and confidence intervals. So the good news is we're not going to be kind of doing it to the extent that we have been, but it's still going to be floating around in the background of what we're doing. So I'll make a lot of references to things we've already done and try to relate it, but regression is going to be a lot less computational and a lot more like interpreting statistics that we see. Okay. So we've talked about previously measures that try to pick up on the relationship between an X and a Y variable. Right? So we said we had the correlation coefficient and the covariance. If either one of those was positive, that meant that as X got higher, Y tended to be higher as well. And then if it was negative, as X got higher, and that Y tended to be lower. Right? And if it was almost zero, that meant there was really no relationship between this X and Y variable. Okay? So we're going to start moving more towards being able to identify a causal relationship. Now, we won't get there in this class. It would take a little more, probably like an advanced stats class to pick up on causal relationships, but we'll at least start moving closer to that in that direction. Right? So the way we're going to do this is using something called linear regression. Okay? So I said it's a review here, but we're not reviewing it. It's just kind of how we would review the concept. So it's going to follow the same kind of procedure, or the same principles would apply as would the correlation coefficient or the covariance. The only difference is we're going to basically have this equation where we assume that Y is a function of X. So we can get kind of some nice visuals with linear regression. Because really what we're thinking about is if I had this X variable and this Y variable, I want to know what's the relationship between them. Okay? So I'll say, okay, Y is going to be some function of my X variable. I'm going to have some intercept and I'm going to have some slope. Right? I don't know what those values are yet, but A and B, well, eventually we'll see we can get these values from Excel and we don't have to kind of do the computation by hand. Okay? So if you remember going all the way back, we talked about the very first thing about identifying the relationship between two variables was we could come up with something like a scatter plot, right? So it shows us kind of like where all the data is. Imagine in Excel, I could have two columns. One is my X variable, one's my Y variable. I could plot every single observation on this graph. Once I do that, I then could try to come up with what we might call the line of best fit, right? So maybe you've heard this before. I feel like, I don't know, this is like I feel like in high school science, I feel like for some reason I remember like ACT or something had on there, right? But if I had a scatter plot, this line that best fits the data is going to give me a pretty good idea about what the relationship is between this X and Y variable. So that line will have an intercept A, and it will have some slope B. Okay. Now what that slope is just kind of my change in Y over my change in X. Or another way I can interpret this, once we start kind of getting into this, is, well, I'll hold off on that for 1 second. So what we're going to try to do is get this line of best fit, okay? So that, you know, if I was to use this equation, once I have some values here, right, for A and B, I could just start plugging in different values for X and come up with a predicted Y value. Like based off the data, based off where I think that intercept and slope is for this line of best fit, I could start putting in different X values and come up with predicted Y. So you can kind of think about, when we're doing this linear regression, we want to be able to predict the value of Y using our X variable. Okay? And that's really what that line is telling me. If I were to plug in this value for X, it would give me this predicted Y value. Now you can kind of see here, I'm going to be a little off, like the actual observation. If I look at the actual observation that had the same X value, notice my predicted Y is a little bit off of what that actual Y value is, right? So we're not going to be perfect, but we're going to be pretty close. Right? We're going to be pretty close if we use this as our line of best fit. So another way to think about this is if I were to see a 1 unit increase in X. What the slope is going to tell me is that for every 1 unit X increases by, B is the amount that my predicted Y will increase by, right? So if I went from 1 to 2, the difference in the predicted Y would be whatever that slope is, right? Because instead of multiplying by 1 and I multiply by 2, I'd be adding it in there 2 times. So I'll use that marker, I'll use the blue one. So if my slope is B, what it's really telling me is that for every 1 unit change in X, that slope is the amount that the predicted Y value would increase by. Okay? So it's kind of the setup of what we're doing. We're trying to get this line of best fit wherever, like let's say we did it by hand, we could then figure out what the intercept value was and then what that slope value was. Okay? Now, we're not going to draw by hand. That's not a very technical way of doing this, right? You don't just eyeball the data. There's a way that we can actually use statistics to come up with what that intercept and slope value are. So we'll talk about that a little bit more here. Okay? So some terms that we're going to use is when I'm thinking about that regression equation, if I can get this to go back, there we go. That Y variable, or my left-hand side variable, we will call the dependent variable. It depends on the value of X, right? So the Y, the dependent variable, the left-hand side variable, all kind of names I'll use to kind of reference that referencing the same thing. The X variable, or that variable that was on the right-hand side that we're using to try to predict Y, we're going to call that the independent variable. It's changing independently. And as it changes, the variable that's dependent on it, Y, will then also change as a result. Okay. So once I have this linear regression equation, I have values for X and Y. I can use regression analysis, to come up with what the values are for that intercept and that slope. Now, I'll show you how you would do this if you wanted to do it by hand, although I doubt any of you will want to once we work through it. And then we'll kind of take a look at how we do this in Excel. Right? So if I'm thinking about kind of a very similar setup, but this is the scatter plot I see. And let's say I draw my line of best fit. What would be true about the slope for this linear regression or for this line of best fit? It's going to be negative, right? As X gets higher, the values for Y tend to get lower, right? All right, so I could come up with that intercept and that slope. The slope would be negative. But if I had something here, well, if I had a horizontal line of best fit, that would actually have a slope of 0, right? So that would represent there's no relationship. As X gets higher, Y is kind of just moving all over the place. Doesn't really tell us, what Y is going to do. It looks like here that Y doesn't depend on the different values of X. Okay. And of course, we've already did the positive relationship. Right? If I got an upward sloping line of best fit, my slope would be positive. We already kind of looked at one that was negative. I don't know why I put 2 on here, but I think I know I did. Because we can often see linear relationships, right? Where my line of best fit would be a perfect line. But there may be data that looks something like this, where if I try to draw this line of best fit through here, I'm going to be off for a lot of these values. If I could just draw any line, I probably could draw a line with some curve to it, or a quadratic, right? Kind of looking at kind of introducing a quadratic term to make sure that I get a line that better fit this data. Now, we're not going to do that in this class. This would be something that we talk more about, like nonlinear relationships would be something that you might see like in an advanced stats class. But you can do it, right? So you can imagine if I'm, my dependent variable is something like stock prices, I really might want to use different X variables to try to predict those stock prices. Not every relationship is linear. And so if I really wanted to accurately predict where those are going, I might have to use something that's nonlinear. But for us, we'll just keep everything linear. Okay? So, we could do convex relationships as well. All right. So returning to our linear regressions. Okay. We're going to, I think I'll use the visual here. So earlier I kind of said, if I plugged a value in for X, let's say I plug in 9 to this equation, whatever the values for the intercept and slope are, I get my predicted Y. However, the actual observation, I'm a little bit off, right? So for every observation, I'm going to have an error term, right? Maybe I had an observation up here, so I come up with a predicted Y value. Right, there's my prediction. Here's the actual Y value. So here I have an error term. Right? So my error term, or what I'm writing as this epsilon, right, is basically just going to be the difference between my actual Y and my predicted Y. So here you can kind of see my predicted Y is less than the actual Y, right? So my error term would be positive. Here my predicted Y is greater than my actual Y, so that would make it negative. Right? So I can make errors in both directions. Right? But what I want to do is find the line of best fit. So the line of best fit is essentially the line where I'd be making the smallest amount of errors. If I chose to a line of best fit down here, well, I'm going to be making huge errors for every observation. Right? My predictions are going to be garbage. So we want to try to somehow minimize the sum of all those errors. The problem is, if I add these error terms up, what's going to happen? Well, the negative errors are going to kind of wash out the positive errors, right? I mean, if it worked out perfectly, maybe I end up even looking like I have the sum of all the errors is 0. But I don't really care what direction I'm making the error. I just care that I'm making that size of an error. So what might be something I could do so that I can kind of deal with this issue? So if I don't really care about the direction or the sign, I could take we've done it in Excel for the last couple of things. Just take the absolute value, right? I don't care about if it's a negative or a positive error. I just care about the size of the error. The problem is the absolute value won't completely if we're going to do kind of ordinary least squares regression, which is what I'm going to be introducing to you, we're also not just going to take the absolute value, but let's say we had like really, really big errors. We want to over penalize our line of best fit if it makes really, really big errors, right? So we're then going to basically add up all of these errors for every observation. I starting with 1 all the way to my last observation in my sample data. I'm going to square that error so that it makes it positive and it really over penalizes big errors, right? 1 squared is still 1, but 2 squared is 4, right? So as I get further and further away from the actual Y value, it blows that number up even more, okay? So what we're going to try to do is minimize the sum of all of our error terms squared. So how can we do that, right? Well, something that probably most people want to, and I guess just to hammer home this idea of the error term a little bit more, if I'm writing out my linear regression equation, I'll usually show it to you in a version like this. So the actual y values are going to be my predicted y values plus some error term. Now this error term is going to vary for every observation. For instance, let's say X was, I don't know, your schooling, like your years of education that you get, and Y is your income. Well, I could tell you a certain number of years of school, and you could tell me that person's predicted income. But if I try to use this predictive equation for Bill Gates, I'm going to be way off, right? He's got a huge error term. And for other people, right, maybe the error term works in the opposite way. They got a certain number of years of schooling, and they just completely dropped out of the labor force, right? So their actual income would be zero, and I probably predict something positive. So the actual Y value is the predicted Y plus some error term that's specific to every single observation. So we're never really initially ever going to observe that error term until we come up with our predictions. We could like parse out what it is. Right? And that error term is basically going to capture all these other factors we haven't accounted for. Right? If I want to know about the relationship between years of education and income, well, I'm not capturing things like, I don't know, what country does the person live in? Or I'm not capturing things like, what's the experience level of the individual, or any of these other factors. And so all those factors will be included in that error term. Okay. So, excuse me, I am going to, we already kind of looked at this, right? Thinking about what the errors look like. And I doubled these slides, so I'm going to skip that. So we've got all these errors. So we want to minimize the sum of those squared errors. So how do I choose A and B? I want to choose A and B such that I'm minimizing the sum of the squared errors, right? And remember, all A and B are is the values for my intercept and my slope that would give me this line of best fit, right? This line that would minimize the sum of my squared errors, right? So I can rewrite my error term. That's just the actual Y minus the predicted Y. We know that to make those predictions for Y, we're just going to use this equation, A plus B times the X value. Well, now Y and X are actual values that we observe for observations 1 through N of our sample. So we'll have some actual data and values to use there. A and B are going to be two values that we want to pick that minimizes this equation. So we can use some calculus, right? I'm not going to make you use it every single time, but that's where this is coming from. We would take a derivative of this function in respect to A, take a derivative of this function in respect to B, set them both equal to 0, and then solve for those two unknowns. Two equations, two unknowns. If we do that, we get something like this. Or you could rearrange this equation to make it a little bit different. And when they used to have to do this by hand, which can't even imagine, right? They might use a format like that. It's a little bit easier when you're entering it into your calculator. Okay. Now, I'm never going to make you do this by hand. I think maybe if we have time next week, I'll show you how we would do it in Excel, just to kind of prove to you that it would give you the same thing that the like behind the scenes built-in, I guess, function you would call it in Excel is doing. But you can imagine how we could do it, right? If I have a column with all the X values, I could just subtract the mean from each one. I then have another column of all the Y values. I subtract the mean from each one. I then multiply those two values by each other. I've got a whole new column that would represent this for every observation. I then add them all up, right? I could do this in Excel. I can kind of envision maybe how I'd break this down step by step. But we don't have to, right? Excel will do all this work behind the scenes for us. So, these are some steps. Don't worry about these. I'm not going to make you do that. But I may just show you just to kind of prove to you we could do this step by step if we wanted to. Instead, we're going to use this built-in tool in Excel. So I'm going to show you an example in these slides first, and then I'll show you how you add this tool into Excel and how you would actually use it. Okay? Any questions kind of up to this point, or kind of grasping the general idea of what we're trying to do? Right? So let it come down here. I'll hold off. I had a thought, but I think I'll work through this a little bit more, and then I'll release that thought. So I had this data. It's like this huge survey data set, and it was kind of older. I think maybe it's like, what was it, 1997? So 24 years or something. So it's pretty old. That's why if you're looking at this median income, it's pretty low. but also it was only looking at younger adults. I think it was like 18 to 24 or something like that. And so the income is a little bit lower than what you might expect, right? But I had this idea, I thought maybe it would be interesting, maybe kind of an interesting one. It also had this variable about drug use, right? So we've got the number of days someone uses marijuana, and it also has the income level, right? So what we could do is think about maybe like some, I don't know, politician somewhere is like, oh, people stop using drugs. So we're gonna try to show like why they should, right? This is bad for productivity. So we've got the individual's income, and we could think it's probably could be a function of the number of days they use marijuana. So we could come up with this predicted income if I can get predictions, right? Or shouldn't say predictions. If I can get estimates for my intercept and my slope. So when Excel's doing all this behind the scenes, trying to give us these values that minimize the sum of the squared errors, it's coming from sample data. Excuse me. So it's still just an estimate. So just like we had a sample proportion, which was centered around the true population proportion, that was not straight at all. We're gonna be looking at an estimate for the slope, which we know should be normally distributed around whatever the true population relationship is between this X and Y variable. Okay. So we run this regression, right? And I'll show you how to do that in Excel in just a second, but you can also use other programs, right? So have any of you guys had to use like SAS or anything in any of your classes? Probably not. This is probably any of the classes that you upper level courses you would. This is probably a prerequisite for it. So SAS or sometimes Stata is another program that's used. So I use Stata a lot, but I'll show you how to do it in Excel, and it tells you the same thing. So it doesn't really matter, but it's got a lot of information here. For the sake of what we're going to do, especially today, we're really going to focus only on kind of this coefficient column. Okay. So this program, instead of calling it the intercept, calls it the constant. Those two terms are interchangeable. Okay. So it's giving me the values for A and B, right? Here's the slope on my X variable. Remember the equation that we were thinking about was right here. So how do I use these? Right? So, okay, that's great. I know the relation or the slope is negative 253, but what does that mean? Well, remember earlier, I was saying we can think about that slope value is really telling you the predicted change in Y from a 1 unit change in X. Right? So that's always how we're going to interpret that slope estimate, or that slope coefficient is what we sometimes call it as well. So that negative 253 slope coefficient is saying that if somebody uses marijuana 1 more day a month, their predicted income would decrease by what? Negative 200, or sorry, not negative, it would decrease by $253. Right? And that really makes sense here, because if I plugged in like, well, I'll do the easiest one. If I plug in a 0 here, my predicted income will just be the intercept. If I plug a 1 in here, it would be the intercept plus just that slope, right? So every 1 unit increase is just going to increase my predicted Y value by whatever that slope coefficient or that estimate for the slope is. Any questions on that general interpretation? Okay, so I think I have that on the next slide here, how you would interpret that variable, but it's always a 1 unit increase, which for us here is 1 more day a month. And it's associated with the expected kind of change in Y, which our Y was income of whatever the value was. And here it was negative 253, so decreasing by $253. How would we interpret, and also I should, before we continue, right? We are walking before we can run. There's a lot of issues with using this to make decisions, right? There's probably a million other factors correlated both with income and also, people using marijuana that wouldn't, we might be picking up the effects of those things, right? So the other example I always give is thinking about murder rates and ice cream sales. If I run a regression with those, you get a pretty sizable effect. But it's because when it's hot outside, ice cream sales go up, and we tend to see murder rates go up as well. So it's this outside factor we haven't accounted for. Now, next week, we'll talk about how do we account for all these other factors. But for now, I might even introduce it right at the end of class today. But for now, we're just going to kind of have this naive regression where we only are thinking about one other thing being able to predict Y. It's likely we need 10, 20 things to predict Y, but we're starting out with just one. Okay? How would I interpret the intercepts? The intercept is always going to, we can interpret it. It won't always be usable. So I'll give you an example here after this that I think will kind of show you why sometimes the intercept will have a really weird interpretation. So the intercept is basically going to be the predicted value for Y, or in this case, the predicted value for income, if our X variable is equal to 0, or if the number of days someone uses marijuana each month is 0. And I kind of already showed you why. So if I plug a 0 in here, my predicted income just becomes, well, 0 times anything is 0. It's just the intercept. So the interpretation of our intercept is always, if this X variable is equal to 0, the intercept is my predicted value of Y. It's kind of like my starting point. You want to think about it that way. Any questions here up to this point? All right. So I'll give you another example and show you why sometimes the interpretation on the intercept is really bizarre. Okay. So if we'll stick with kind of the same idea. So if I try to predict income with age, maybe I think that as people get older, right, you accrue more skills, you tend to see, your income increase, right? So maybe I want to know, how much is my income going to increase every additional year I get older? Right? Well, you think about what that data might look like. Probably going to look something, maybe like this. Okay. And this is kind of my 0, 0 point. So I've got all this data. I'm going to draw my line of best fit. All right. So I draw this line of best fit. It's not straight at all. Right. And my intercept's down here. Maybe I run this linear regression and I get negative 10,000. So if this was negative 10,000, yes, oh, sorry. If I see the estimate be negative 10,000, how would I interpret that? What would be if somebody is, if my X variable is equal to 0, the intercept is my predicted income. So here, if someone's 0 years old, their predicted income is negative 10,000. There's a lot that doesn't make sense about this. We never see someone who's 0 years old. You can't earn negative income as far as I know. Right? Unless, I guess if you're, I don't even know how you would do that, right? Unless you just destroy things at your job and then owe them money at the end of the day. But, right, the reason why we would still interpret it that way, it's just sometimes we have these scenarios where it's weird because all of our data, we don't really, I think the last time I remember, like, you can't legally work unless you're over 14, I don't think. I think maybe there's, you can get paid under the table, but that's not going to show up in any data set, right? So we never see anybody in these age groups, so it's going to be kind of a weird interpretation, right? Now, what could I do? Maybe that would be a little bit more useful. Well, let's say I know that you can't work unless you're 14, or whatever, whatever the state is, whatever their law is, right? Or you have to have a permit or something. So maybe I say, okay, look, I'm going to use that X value of 14 because I know that's really the lowest the age I'm going to see is the lowest the age I will see is going to be. So what I could do is, if I plugged 14 into here, came up with that predicted income, I could almost like think of that as, well, this is really my starting point, right? Technically, negative 10,000 is if I start having babies work, right? Maybe it does make sense that babies would have negative income. Right? They probably would destroy more than they produce. So I could plug that lowest value I know I'll actually see in practice into that equation and then come up with really what my intercept in practice would be. Right? But nonetheless, we would still interpret the intercept value we see from the regression results the way that I just did it, right? Someone with 0 years of age, that's how much their income would be, the predicted income would be. Okay? So I just want to mention that because sometimes maybe that next Excel assignment, which I should get that posted up tomorrow. I was going to do it yesterday, and I ended up things happening. I didn't end up in the office yesterday, and so I'll get that posted today. But it would have been, it's on regression, so it's not like you could have really started it yesterday anyways. But you might have an interpretation of an intercept there that just ends up like this example. It's kind of weird, all right? But that's still okay. So where are we at with time? Oh, okay. I think I'll show you this, and then we'll take a look at Excel, and I'll show you how we actually run these regressions. Okay. So I said that hypothesis testing and confidence intervals will be floating around in the background. So if we think about that coefficient B, I already said the sample coefficients that I'm calculating, Excel's calculating for me, should be normally distributed around whatever that true slope coefficient is, or true slope is. Sorry, I shouldn't call it a coefficient, it's the population. Well, if we had proportions, right? We could do some hypothesis testing there. I can do hypothesis testing with coefficients as well. And the ones that we're going to see are really the same three, right? Right, left, two-tailed test, right? I say most of the time here, there are situations, like if you were to kind of continue taking a stats course, you would talk about these probably, where you could test to see is something greater than 0 or is it less than 2, or like you use values other than 0. Most of the time, I mean, even at a very high level, 90+% of the time, you're always going to use the same hypothesis test, which is that slope is equal to 0. So if I'm thinking about the slope coefficient or even the intercept coefficient, the null hypothesis will always be for our class that's true slope for the relationship between x and y is equal to 0. Okay. So we have this hypothesis test. We're always going to have the same null and alternative hypothesis. We're essentially assuming that there is no relationship between x and y. We're stacking the deck against ourselves. And then if the sample evidence shows us that the coefficient is positive or negative, then we could maybe say that there's a significant relationship between these two variables, right? Because we think about it, let's say I've assumed that this true relationship is 0, but I see a sample coefficient, slope coefficient way out here, and I end up with a p-value. Now it's a two-tailed test, so I would actually technically have a side over there as well, but if I take this, multiply it by 2, if my p-value is less than alpha, I can reject the null, just like before. So when I look at these p-values, I can reject the null if they're less than alpha. And if I reject the null, what I'm really saying is I reject, say it this way, I can reject that there's no relationship between those two variables. Or said differently, I found strong evidence that there is a relationship between those two variables at whatever level of confidence my alpha corresponds to. Okay. Any questions there? We'll keep moving. So I said, it's going to be floating around in the background, but we're not going to be calculating test statistics. We're not going to be thinking about critical values. The only thing we're really going to use with linear regression for hypothesis testing is we're going to use a p-value that Excel gives us to determine whether or not we can reject. So the only thing we really need to remember is that only reject if the p-value is less than alpha. All right? I don't have to worry about one or two-tailed tests anymore. It's always a two-tailed test. You assume true kind of slope is always 0. So I just need to get that p-value and make my rejection decision. So if I'm going back here, I go back to my results. Notice here, this program told me that p-value. It was basically 0. So I could say here with any level of confidence that I could reject the null. Remember, the null is that there's no relationship. So I can reject that there's no relationship, where I found pretty strong evidence that there's a correlation between the number of days someone used marijuana and income. Okay. All right, so got our kind of hypothesis testing. We can also calculate test statistics. Now Excel and these other programs do it for us anyways, right? But this is going to be kind of one where I can just get a little bit more, get a few more examples of how, to cover. So we're getting used to interpreting these coefficients. Let's say instead I want to run a regression where I'm looking at birth weight and whether or not the mother smoked while pregnant. Okay. But I hide these results from you. So how would I come up with this test statistic? Well, we're going to have another column, which is this standard error. And the way that we come up with a test statistic and then use that test statistic to find the p-value is simply by taking this coefficient and dividing it by the standard error. Okay. So for now, we don't have to really know how we're coming up with that. I think I'll kind of save that for next class. But, oh, actually, no, sorry. Why was I showing this? So all we're going to do to find that test statistic, or all Excel is going to do, is take whatever that slope coefficient is and divide it by the standard error that you have for that variable. So, I mean, this is pretty easy, right? If I ask you to find a test statistic from linear regression results, hopefully it's very easy. Here, I would take negative 213 divided by 48.9, right? So I don't know, that's about -4, so negative 4.36, I'm guessing, is the value you get if you divide this coefficient by its standard error. Now, if I wanted to interpret this variable, here I've got one that's a little bit different, right? So sometimes we run into these dummy variables. They're just 1, 0. This was the mother either smoked at some point in the pregnancy, it was a 1, 0, she didn't. So here, the way we would interpret this 1, 0 variable is it's the effect or the predicted change in Y from belonging to the group that's coded as a 1. So here, if I was a mother that smoked while pregnant, the predicted change in child's birth weight would be 213 grams less or lighter, right? Negative 213. So if it's a 1, 0 variable, the 1 unit change is going from the 0 to the 1 group, right? Going from a mother who didn't smoke while pregnant to smoking while pregnant would decrease the birth weight by 213 grams. So that's the only other kind of tricky thing we might see show up as I'm working through some examples here. Okay. Questions on that before we keep moving here? All right, so we've got all this good stuff. R squared, I think we'll talk about that next time as well. I have, and this isn't up on Canvas yet. I'll post whatever we do in class today. Okay. So just kind of watch me as I walk through. If you've got your laptop also, I'll try to help you add something into it that will be beneficial for that last Excel project. So here I had all that COVID data. I don't know, I got kind of interested. So I found the number of new cases in each county from June to October. And I then went out and grabbed the percent of the population in those counties that had been reported as vaccinated, right? So what's that correlate, or what's the relationship? Can I predict the number of new cases a county sees based off of their kind of vaccination percent? Now, I didn't put in as much effort as I should have, because I probably should have went out and found population data so that I accounted for the populations of these counties. But maybe that's something that we'll do next week. I've got some additional data layer, and I think I can merge that in. We might be able to kind of piece by piece get closer and closer to taking a look and see how, t-tests were great, and they kind of show us like some weird stuff with the code that might go against our intuition. But I wasn't using linear regression, which is a more powerful tool. So how does that change things? And then finally, next class, we'll also talk about how can I control for other factors. We'll have a little more discussion at the end of class today about correlation versus causation. So I want to use the number of new cases as my Y variable and try to predict that with the percent of the county that's vaccinated. Okay. So I have a linear regression tool in Excel, but it's usually not like default on my, if I, let's say I just went out, download Excel on my computer, it wouldn't be there. Right? So on a PC, if I go to File, and all I see right now are Macs, so I will try to walk you through it with Mac. I believe on a Mac, you don't have to have Excel open, but at the very top, you have like a tools thing at the very top. If you click on that tools, I think you should have something there that says add-ins. Excuse me, if you're on a PC, you have to go to options, and then I can see the add-ins. Right? So once I see those add-ins, I click on it. I'm not sure if this is true on a Mac. I don't think you have to click on the manage add-ins on a Mac. I think it might just, once you click on add-ins, it shows them to you. If I hit manage my add-ins and hit go, I need to make sure that analysis tool pack is checked, right? Once if it's unchecked, it won't show up. If it's checked, it will show up for me, okay? Is anybody on the Mac walking along with me? Was that a fair description? No? Okay. I say you might have to do it for other classes too. There's some other, like I only have 4 that are showing up here, but there's plenty of other ones you can get as well. So I'm gonna hit OK. And now once I get that analysis tool pack added in, I go to data. It should be all the way over on the right-hand side there, this data analysis. If I didn't go through the steps I just did, you wouldn't see this. If you are having any issues kind of getting this downloaded, please reach out as soon as possible. For a Mac, you probably could Google analysis tool pack. There might be something out there. I should probably switch over my line by line because at this point, more people have Macs than PCs. But if you're using like a university computer, a lot of those are PCs. And so I have those steps up there for you as well. Okay. Any questions on that? So on a PC, file, options, click add-ins, manage the add-ins, add the tool pack, right? Click check mark it. On the Mac tools, there should be an add-ins option, and you kind of are searching for that analysis tool pack to add in as well. Okay. So if I click that data analysis, I've got all these different options I can do. Right? So notice it even has things that it already had built-in functions for, like my correlation coefficient. We had an equation for that. It has a built-in function where you just have to select the data. It's really doesn't really save any time. I don't know why someone wasted time to put this in the analysis tool pack. Probably because at one point it wasn't a function in Excel, like in the raw version or the default version. So we'll go down here. We've got regression and click that, hit OK. My Y variable is going to be this number of new cases. So I select the label, right, or the name of the variable. I'll show you why that's important here in a second. Control Shift or Command Shift on a Mac, hit the down arrow, hit this arrow, it pops me back up to the top. The X variable that I want is just this % of the county vaccinated. So I select that. I've selected my labels, so I have to make sure this box is clicked. If I don't, Excel will get mad at me, right? It says it won't do anything with non-numeric data, which, okay, that's fair enough. So I tell it that I selected the labels, because that helps once I see the output so I can see what those actual variables were. I always put my output on a new worksheet. You can put it on the same worksheet and like select, like, oh, I want to put it right here, right? But I generally will always put on a new worksheet just because I think it's easier to keep things separate. And then we don't have to mess with anything else here. We don't have to click any of this other stuff, okay? So we hit OK. I get this output, all this stuff spit out at me. All I have to really look at here, and we'll talk about some of the other stuff in here we might want to use, but for now, we are only going to focus on this coefficient, this coefficient column, and then this p-value, okay? So I've got my coefficients. What this is telling me, remember, is that, oh, I didn't write it down. So what we did was cases as a function of vaccine percent. Right? So a 1 unit change in my X variable, which would mean 1 more % of the population getting vaccinated, would change the predicted number of new cases by whatever that slope is. So 1 more % of a county getting vaccinated actually increases the number of new cases by about 100 people. Right? So it seems kind of weird. Right? But this is where we then have to have a discussion. When you do a simple linear regression like this, you're picking up the correlation. I said we're moving towards causation, but not yet, right? So, and, one thing that could be the case is, just like with the murder rates and ice cream example, maybe a lot of the counties that are getting vaccinated at higher percents is because there was just more general at risk in those counties. So maybe it's that it had a higher population, right? Or it was more dense population, I should say, right? Or maybe it was lower or higher income classes, right? Which would be heavily correlated with the percent of people that get vaccinated, but also heavily correlated with the cases. So it could be this third outside factor that's really driving both of these. So even once we get to this point, we need to take a step back and say, it's still just evidence of a correlation. So I can't like say that the vaccine is causing people to get COVID yet. I shouldn't say yet. I can't say that, right? So the next step would be, I want to control for all these other factors, right? I want to maybe say, how can I pick up that relationship while holding constant the population density, while holding constant the average income in the area, by holding constant all these other things. So that's the next step, right? But there's still one more thing I want to talk about with this simple linear regression first. Okay, so I can interpret these coefficients, but I also want to know, just because I find a value doesn't mean that the true population relationship isn't anything different from zero, right? Because let's say, the true relationship was zero and I saw a positive value, but it's, it was fairly likely for me to see that based off the sample size or something. Well, I can check to see, can I reject that null hypothesis? So I look at these p-values, and for the percent vaccinated, that p-value, when I see e to the negative 17, that means move the decimal place 17 places to the left. That p-value is basically zero, right? So if I have a p-value that's basically zero, I can reject the null at any level. So here I did find a positive correlation, and I would say that it is statistically significant, right? Or at any level of confidence, I could reject the null and say that I did find evidence there is a relationship between these two variables, right? I reject that there's no relationship. Any questions on anything there? So, I don't even know if I have it. I should have it here somewhere. I copy and paste the wrong things. Yeah, I did. So I think what I'll do is maybe get us out of here a little early today. So we went over everything in Excel. I showed you how to do that. We talked about p-values. So all they're going to do that you won't, I'm trying to keep you in the other section on the same pace. Well, I'll just show you in Excel. Let's see. Well, so let's say I didn't do this number of new cases variable. Let's say that I take out this variable here. And I want to know, how is that vaccine percent correlated with October cases? But I want to hold constant kind of where those counties were at in June, right? Kind of where their starting point was. Okay. So what I can actually do is go to my data analysis tool, regression. My Y variable is, what was the number of new cases or number of cases in October? And then for my X variable, I can actually select multiple variables. So I'm going to select metro, percent vaccinated, and the number of cases they had in June. Okay. So I'm going to then Control Shift, hit the down arrow, hit that little arrow, hit OK. And notice I can actually, have several right-hand side or several X variables. Okay. So what that looks like, right, is I can run, and I'll write this out more generally. I can run a regression where I have several X variables there on the right-hand side. Okay. Now the math behind what's going on becomes much more complicated, but the thought experiment is, what is the relationship between X1, this variable X1 and Y, holding all these other variables constant? And to do that, you got to know some linear algebra and deal with some matrices, but you can do it, right? And programs can do it for you much easier than you could ever do it by hand, okay? So now the interpretation of our coefficients is exactly the same. It's still a 1 unit increase in X causes whatever that slope coefficient estimate is, predicted change in Y. But the only additional thing we now say is holding everything else constant. Well, that's pretty powerful, right? Because you can imagine, like now, where did it go? Here we are. Now, when I'm looking at that coefficient between the percent of the population vaccinated, here, I'll make it bigger so we can actually see it, right? Now the interpretation is, notice, and we'll talk more about this next week as well, when I don't include things that are important, it biases my coefficient estimates. This is the idea that it'll look like ice cream sales are highly correlated or causing murder rates, right? But if I can add in that control of temperature, it basically goes away and becomes insignificant, right? Here, when I added in whether or not the county was in a metro area, so that was just a 1-0 variable, and I controlled for like where their number of cases was starting. Now notice if the county gets 1% more of their people vaccinated, now it's starting to decrease the number of cases they see in COVID, right? Holding constant these other two things. So it would be like this: 2 counties, same number of cases in June. They're both either in a metro area or not, but one of them gets 1% more of their population vaccinated. They could expect their COVID cases to decrease by 14. So I've only included 2 controls here. You can imagine if I can throw more things in, you get this thought experiment, which is like, hold all, like you could never find 2 counties with the same population, same average income, same demographic breakdown, same, like go down this list of all this data you could gather, but one of them has 1% more of the county vaccinated. You could never find 2 counties to fit that description. But based off of variation you see in the data for these variables, the linear regression essentially is doing that for us, creating that hypothetical thought experiment for us. So it becomes pretty powerful, right? You can do some pretty cool things with that. So hopefully we'll go through more examples next week, Monday and Wednesday of next week, where we look at multiple linear regression. I'll talk a little bit about omitted variable bias, and I'll talk a little bit more about how do we use these results to come up with predictions, right? Just to kind of give, I mean, I don't know how any of you would be interested in this, but maybe it'll kind of spark some interest. So, you know, some of these like advanced stats. So the next one I think is ECON 321. We have a stats course here, but you could also take stats in that department if anyone's, I don't know, you know, if you're a finance degree or something. This is like very powerful. I was mentioning stock prices earlier. Like you can look at historical data, run these regressions, use these coefficients to then predict like where these stocks going to move, holding constant a whole bunch of factors, right? The other thing that I got really bored once, and this might speak to who I am as a person, but I went out and like gathered a bunch of data, like sports betting data, and you can actually, if you account for all these factors, and if there's some factors you think that like the sports bet places aren't doing, you can actually come up with predictions about what the line should be versus what they are, and then kind of compare the results of the two and see like which one of these schemes actually is predicting the games better. And if you can do something better than they are, right, then you could actually make some money, right? So it's really a powerful tool. We'll run through some more examples next week with this, and probably a lot of the review will be mainly focused on linear regression, right? So we've done, I mean, we'll obviously do some hypothesis testing, p-value stuff as well that Monday for review, and I'll get up some videos like I have before of me working through one of the practice exams next week. But yeah, we'll kind of just be focusing on regression and then transitioning into review probably towards the end of class Wednesday and then on Monday as well. Okay. Any questions for me before we get out of here? Okay. Okay. I posted an announcement. My office hours have been kind of screwed up, so I will be in my office. Jeez. I will be in my office on tomorrow from 10 to 2, and then Friday from 2 to 3 as well. Right? So if you want to stop by, since I wasn't there yesterday as long as I expected, and I wasn't able to be there this afternoon, we'll have those office hours. Other than that, we'll have a good weekend. I'll see you guys on Monday. Okay.